Dear students, welcome to the EPG Pathshala. I am Dr. Gurmeet Singh, Professor of Chemistry in the University of Delhi. Today we are going to discuss about the module Chemical Force Microscopy, under which we shall talk about the introduction of this topic. This comes under the paper of Surface Analytical Technique Part 1. After going through this module, you should be able to understand the basic concept of the CFM, necessity of CFM, that why was this required, what is the historical background of this. You will be able to understand this as well. What are the advantages of this, and what are the prime uses of this in nanotechnology, and finally the limitations or disadvantages, as we call these. In introduction, we will read that it's a variation of atomic force microscopy, which has become a versatile tool for characterization of materials surfaces. With AFM, the structure morphology is probed using simple tapping or contact modes that utilize van der Waals interactions between tip and the sample to maintain a constant probe deflection amplitude. That's called a constant force mode, or maintain height while measuring the tip deflection, that is constant height mode. Intermolecular forces affect a variety of problems in condensed phases, extending from capillary and lubrication at microscopic length scale, or micelles and membrane self-assembly ones on the microscopic scale, to molecular recognition and to protein folding at the nanoscale, which is a very important area. Understanding these phenomena, regardless of the length scale, we will find that this requires a detailed knowledge of the magnitude and range of molecular forces. Atomic force microscopy is a powerful tool for probing intermolecular interactions because it can resolve forces with piconewton sensitivity. That means at a piconewton level, one can analyze this and has a special resolution of nanometers range. These features enable AFM to produce nanometer to micron scale images of, for example, topography, adhesion patterns, frictions, and compliance, and thus make AFM an excellent characterization technique for fields ranging from material science to biology. Chemical force microscopy, which we had abbreviated as CFM, and the slide was on introduction. Chemical interactions can also be used to map pre-patterned substrates with varying functionalities. Scanning of a surface having varying hydrophobicity with a tip having no functional group or no functional groups at all attached would produce an image with no contrast because the surface is morphologically featureless. Non-covalent intermolecular interactions shape the majority of microscopic processes in chemical, biological, and artificial systems. Examples range from lock and key interactions that define molecular recognition to interfacial adhesion and friction that define performance and wear of industrial equipment. Moreover, as nanotechnology begins to set the pace of modern technological advancement in areas as diverse as telecommunications and biomedical engineering, the prominence of intermolecular interactions will only increase. Potential technological and scientific payoffs from the intimate knowledge of these non-covalent bonds and the nature of their failures are enormous and could range from better drugs and medical imaging agents to wear resistance interfaces, then to super strong and reversible adhesives. Historically, non-covalent interactions have been relegated to the second place in chemistry, and most efforts concentrated on understanding covalent binding and chemical reactivity. Researchers studied non-covalent interactions mostly using macroscopic techniques such as calorimetry, surface tension studies, IR spectroscopy, chemical equilibrium, virial coefficients studies, and elastic modules. These indirect measurements have provided a wealth of the information about non-specific interactions, yet understanding the true nature of the non-covalent bonding still requires a direct measurement. A simple back of the envelope estimate pegs the strength of a typical non-covalent bond to the range of the maximum gradient to a typical interaction potential, which produces estimates to the tune of 10 to 1 nano numeral intervals. Variations of the surrounding medium only increase this spread. Experimental techniques that could measure forces in the range under a variety of ambient conditions and solvents have only become available during the recent decades. Specifically, three techniques are capable of such measurements. These are surface force separators, optical and magnetic tweezers, atomic force microscopy, etc. Of the three techniques, only AFM possesses both the sub-nanometer spatial resolution and piconewton force resolution necessary for characterizing the strength and spatial distribution of intermolecular interactions. AFM measurements use sharp microfabricated probes attached to the force sensing cantilevers with spring constants ranging from 0.1 to 100 newtons per minute. These probes, coupled with angstrom level distance, these measurements and positioning accuracy give AFM and technical capabilities for measuring specific interaction forces a great advantage. However, the utility of standard AFM setup for measuring specific forces is severely limited by the unknown chemical composition of the AFM tip. The ability to probe interfacial forces with nanometer scale resolution is critical to developing a molecular level understanding of a variety of phenomena, including friction and boundary lubrication, adhesion, and fracture at interfaces, double layer forces, and colloid stability. Significantly, the absolute force resolution in AFM can be several order of magnitude better than the weakest chemical bond. The resolution suggests that it should be possible to probe individual molecular interactions. However, the specific chemical group on a tip interacting with the surface are typically ill-defined. In addition, the contact area of the tip on a surface can be quite large because of the finite tip curvature and tip deformation resulting from surface forces. Although for chemical microscopy it provides no scale formation about the kind of friction or adhesion or compliance, it has been able to probe directly the specific chemical groups that ultimately determine these phenomenon at the molecular level. To overcome this inherent limitation of AFM, we introduced the concept of chemical modification of probes to make them sensitive to specific molecular interactions. By utilizing chemical functionalized tips, force microscopy can be used to number one, probe forces between different molecular groups, B, measure surface energetics to a nanometer scale, and C, determine pK values of the surface acid and base groups locally, and D, map the spatial distribution of specific functional groups and their ionizable station. This ability to discriminate between chemically distinct functional groups has led us to name this variation of AFM, chemical force microscopy, written as CFM. Now comes the question of what is the necessity of CFM. Atomic force microscopy is an imaging tool used widely in fundamental research, although it has, like other scan probe microscopies, it has provided only limited information about the chemical nature of the system being studied. A disadvantage of AFM compared with the scanning electron microscope is that the single scan imaging size is done with this. The scanning speed of AFM is also a restriction or a limitation. Traditionally, an AFM cannot image or scan images as fast as a scanning electron microscope can do, requiring several minutes for a typical scan, while an SEM is capable of scanning at near real time, even though a relatively low quality can be obtained. The relatively measured rate of scanning during AFM imaging often leads to the thermal drift in the image, making the AFM microscope less suited for measuring accurate distances between topographical skin on the image. AFM images can also be affected by hysteresis of the piezoelectric material and crosstalk between the X, Y, Z axis that may necessitate software enhancement and filtering. Chemical force microscopy is something very similar to this. And this is what we notice when we study the AFM imaging in similar environments. Such filtering could squash the real topographical features. However, newer AFM utilizes closed loop scanners which practically eliminate these difficulties. Some AFMs also use separated orthogonal scanners as opposed to a single tube, which also serve to eradicate part of the crosstalk problems. As with any other imaging technique, there is the option of image artifacts which could be induced by an unsuitable tip, a poor operating environment, or even by a simple technique of AFM like modification of force microscope or force microscope probe as such. The tips by covalent linking of organic monolayers that stop in well-defined functional groups enables direct probing of molecular interactions and imaging with chemical sensitivity. This new chemical force microscopy has been used to probe bond and frictional forces between distinct chemical groups in organic and aqueous solvents. Contact mechanics provide a framework to model the adhesive forces and to determine the number of interacting molecular groups. Scan of a patterned surface with regular tip where no functional group is going to be there would produce an image with no contrast because the surface is morphologically uniform. A hydrophilic tip on the hydrophilic functionalized portion of the surface causes the cantilever to bend due to a strong interaction which is detected by the laser deflection, therefore producing a chemical profile image of the surface. Cantilever functionalization is switched so that the tip is bent when encountering hydrophobic areas of the substrate instead. Now, this phenomenon has been explained in the picture given below this slide, wherein hydrophobic and hydrophilic attractions between the two plates have been indicated.
Why AFM will be used? Atomic force microscopy is generally used to capture 3D topographic images of sample surface. Today it can routinely achieve atomic resolution to identify monoatomic step and ripples in the z direction and resolve lattice orientation and surface defect in the xy plane. In addition to traditional constant and tapping mode, novel modes have been developed to stably control ultra-low imaging force, thus preserving both the AFM tip and fragile sample. These modes also allow precise local stress to be applied to the sample for mechanical, electromechanical, and piezoelectrical studies beyond topography and local force control. Advanced AFM modes allow researchers to capture maps of modules, adhesion, deformation, conductivity, surface potential, permittivity, optical absorption and reflection, electrochemistry, etc. This information is generally captured through multimodal imaging at normal or high speed acquisition rate, which make correlation among different properties possible. In addition, AFM work not only under ambient condition but also in controlled environments including liquid, varied temperature, dry box, vacuum, etc. All these capabilities contained within one single instrument make AFM a versatile platform for investigating highly multidisciplinary research. Therefore, AFM stands out among other techniques for investigation of 2D materials. The applications of AFM for specific research area have been widely reviewed, such as batteries, biological system, polymer, solar, fuel, etc. This work provides a tutorial reviews of AFM's applications in 2D materials for researcher. AFM basics in its most basic form. AFM involves scanning a sharp probe across a sample surface while capturing information about surface properties. An AFM probe is composed of a substrate, a cantilever, and a sharp tip. The substrate is a rectangular chip with sides measuring on a millimeter scale and serves as connection point for the probe. The cantilever protrudes from the substrate, can be triangular, rectangular or other form, and measures in micrometer. The tip, the part that interact with the sample surface and provide high resolution, is at the end of the cantilever and measures in nanometer. The AFM probe is capable of high resolution imaging due to combination of efficient piezoelectric actuation that is used to precisely drive the tip or the sample. The use of sharp tip with optimal mechanical properties and a fast feedback control loop for maintaining used defined tip sample interaction, that is called set point. The piezoelectric actuator together with the feedback loops allow for the tip or sample movement control at the picometer scale. AFM probes with different chemical, geometrical, and mechanical properties are commercially available, each of which may provide different information depending on their interaction with the sample. Probes with nominal and tip curvature radii of 1 and 2 nanometer are now also commercially available.
The applications of this phenomenon. A biological implementation of CFM at the nanoscale level is unfolding of proteins with functionalized tip and surface. Due to the increased contact area, the tip and the surface act as anchors holding protein bundles while they separate. An uncoiling ensues. The force required jumps indicating various stages of uncoiling. The stages are: number one, separation into bundles; number two, bundle separation into domains of crystalline protein held together by van der Waals forces; and number three, linearization of the protein upon overcoming the secondary bonding. Chemical force microscope, it analyzes, of course, force and distance. When the tip is placed in a fixed point on the sample and move in the vertical direction to the surface and then retracted from the surface in place of scanning, the deflection of the cantilever can be measured as it moves. The cantilever is in the repulsive contact region of the cycle, and the adhesion interactions between the tip and the surface one analyzes. The deflection of the cantilever will provide information on the mechanical properties of the material during the part of the approach and the reaction. Forces versus distance. How would the force change with the distance has been shown here in this slide. This slide shows what way the compound is put, how the touching affects touching of the probe, and how from a distance it gets affected, and what way it pulls off near to the surface. There are different areas that you get, and that leads to a plot of CFM. Slope here gives elastic module of soft sample or force constant K of the cantilever. Preparation of chemical tips. This slide shows what way the chemical tips is prepared for number of organic compounds, which includes very many classes, which has amines, alkanes, acidic class, alcohols, and fluorine compounds. And how do they show up has been shown in this slide. How the compound is aligned on the surface. Here the example has been given of self-assembled monolayers on the surface, and what we have is terminal group, we have alkyl chain, and we have sulfur, all allotted, and the compound absorbed on the surface can be analyzed with the help of this. Chemical force microscopy, and what way it moves on the surface, and it is able to analyze the changes in potential. It has been described in this particular slide. The force is increased by the locally causing chemical reaction to the surface by a chemical component. So the changes are shown up in the changes in the potential. Now I'm sure one is very keen to learn about the historical background of this equipment. CFM has been primarily developed by Charles Leber at Harvard University way back in 1994. The method was demonstrated using hydrophobicity, where polar molecules, as example COOH, an acidic group, tend to have the strongest binding to each other followed by non-polar, as example, an ethane, CH3 molecule bonding, and a combination of being the weakest one can take. Conductive atomic force microscopy is a powerful tool, firstly developed in 1993 to study the local tunneling currents through 12 nanometers thick silicon dioxide films. Now, chemical force imaging can be done with the help of chemical sensing or chemical sensitive imaging. AFM probe tips are covered by particular chemical functional groups. We have given the examples of a methyl or NH2 or COOH or more exotic biological molecules too have been studied. Scanned over a sample to detect addition differences between the species on the tip and those on the surface of the sample. Chemical imaging of structures present on the surface due to differences in interactions between the tip and the sample can be studied. The latest force image of a sample patterned with regional terminating in CH3 and an acidic group COH recorded in DI water and air with methyl functionalized tip. In the first photograph, section A, light regions are areas of high friction and corresponding to surface regions terminating in CH3 functionality. Dark regions represent low friction and corresponding to the surface area terminating in COOH acidic functional groups. A B part here shows the high friction, that is light areas, corresponding to regions terminating in COOH groups, while the low friction, the dark areas, correspond to CH3 terminated regions. The images are 100 micrometers into 100 micrometers of size. Advantages of chemical force microscopy. This microscopy, as I said, has a lot of advantages. The tips commonly used for CFM include oxide-coated silicon or Si3N4 tips modified with organosilicon or organosilicon siloxane self-assembled monolayers, abbreviated as SAMs, and gold-coated tips modified with organomercaptans SAMs, directly measuring single intermolecular force in solution. Second, investigating nanoscale heterogeneity in the chemical properties on sample force. A biological completion of CFM at the nanoscale level is the unfolding of proteins with functionalized tip and the surface. Due to the increased contact area, the tip and the surface act as anchors, holding protein bundles while they separate. An uncoiling ensues, the force required jumps, indicating various stages of uncoiling, obviously, division into bundles, bundle division into domains of crystalline proteins, held together by van der Waals forces, of course, and linearization of the protein upon overcoming the minor bonding. Information on the internal structure of these complex proteins, as well as better understanding of the constituent interactions, are provided with this method. The disadvantages of this technique. Chemical force microscopy has some disadvantages, and single molecule force spectroscopy as well as chemical force microscopy both have enabled researchers to map chemical groups and receptors on cell surfaces. But this mapping is not very precise, thereby posing a disadvantage while using this technique. So students, having learned about CFM from various points of view, like historical background, the principle behind this, and the other instrumentation part, let's summarize what you have understood out of this module. CFM imaging can find many uses in basic and applied research, from quantifying the strength of interactions in host-guest systems to identifying surface distribution of chemical modifications or chemically distinct domains in soft materials such as copolymers. A wide range of intramolecular interactions can be studied by this technique called CFM, and analysis of these data can provide basic thermodynamic informations relevant to chemical, biological, polymers, or colloidal systems. CFM imaging of systems such as polymers, biomolecules, and other materials could produce direct images of the spatial distribution of functional groups, hydrophobic versus hydrophilic domains, and the time course of the surface reorganization. Therefore, in conjunction with the adhesion data, CFM can distinguish between functional group domains in organic and aqueous solvents. I hope you would have understood the potential of CFM towards imaging various important areas of chemistry. Thank you very much, please.